All right, for the absorption spectrum, an electron within a hydrogen atom at first exciting states of n equals 2. What energy is required to transition that from the ground state to n equals 2? So we are actually using that same picture that we had on the previous question here. So the energy transition level, well, that's just the delta E. And we're just going to say EF minus EI. In this case, the final energy was 3.3. And we're going to subtract it from the initial, which was a negative 13.6. Okay, so we're transitioning up in this case. So when you do that, you'll notice that the atom itself will gain energy. So we are now adding 10.21 electron volts. So it's actually the same answer that we had previously, but in this case, we're talking about a positive. The atom itself is positive, which means it's absorbed a photon. So that's for A. B, the energy is needed to ionize an electron that's already at n equals 2. So in other words, we're doing an energy transition from the initial being n equals 2, the final being all the way up to n equals infinity. And in this case here, n equals infinity, if you notice, will have 0 electron volts. So final minus initial, we're then talking about, well, its final is 0 electron volts. And we're minusing the initial energy. And because it's n equals 2, we said that was our 3.39 again. So you'll notice that we do end up getting 3.39 electron volts. So that number that you often see on the side there is the amount of energy that it takes to ionize. So that 3.39 would be the amount of energy required for something sitting at n equals 2 to completely ionize. If something's standing at ground state, it would then take 13.6 electron volts in order for it to be ionized. All right, let's take a look at the next one. C. What is the wavelength of a photon that must be absorbed in order to raise an electron from n equals 3 starting at n equals 2? So once again, we're talking about E, the final being energy at 3, the initial being the energy at 2. So we are going from 1.51 being our final, negative 1.51 electron volts. And then our initial, once again, is at 3.39. Negative 1.51 minus negative 3.39, and we end up getting 1.88 electron volts. That's the energy of the photon that was absorbed by the atom. So to solve for the wavelength, we're then saying hc over energy again, just rearranging that energy equation. 4.14 times 10 to negative 15 times 3 times 10 to the 8 times 10 to the 8 divided by 1.88 electron volts, and we end up getting 6.61 times 10 to the negative 7 meters, and as a reminder, that's equivalent to 661 nanometers. So definitely in the visible spectrum.